Wait, this is the fluid experiment cell. Not the system, but the cell. Here you see that this is the coolest thing, $1 million coolest thing. These are all expansion chambers and so on. This is the device by which the crystal was protected after the growth, because on ground it is very easy. You grow a crystal in a chamber, like if this is the chamber, and when the crystal growth is complete, you pull the crystal out and dry it and put it in a desiccator. You can't do that in space. But if you do it in space, the fluid will come out with the crystal because there is no gravity. So the fluid will come out of the crystal and float, which is dangerous to astronauts' life. So they don't want to do that. So we have to develop a technique by which this, after the growth is complete on this seed crystal, this thing actually is electrically driven by motor. This comes down and fits over the seed crystal. And there was a little balloon inside this, which you see here, white thing. That the purpose of the balloon was to push the fluid on the top surface of the seed, here, so that it drives the fluid out and then covers and seal it completely so that it stays there till the shuttle lands on the ground. And then we take this whole cell out and then remove the seed crystal. Yeah. So this is a sophisticated cell. The whole cell probably was a few $1 million, but my wife was very upset on me that why I am wasting public money by doing experiment in space. Why can't I do in the lab? But we learned a lot of things on space experiment. This is the whole optical system. I will not go through that. This is a holographic technique, and you can see that how sophisticated you have the laser beam and you have holographic element, and the laser is here, and the whole system is shown on the ground. We did similar experiments on the ground. This is on the optical bench, but this was contained in this entire unit here. These are the results. The detectivity, the quality of the crystal is determined not only by other X-ray techniques and others, but our main purpose is to see that how good the crystal is for detection. So the term which is used for detection is detectivity, D star, which is a function of how much light you shine and how much you detect. So if you look at the crystal, this is the crystal SL Space Lab 3. This is a macrogravity grown crystal. This detectivity was 0.99. And if you look at this is the 1G grown crystal, this is a seed crystal, detectivity was 2. Pretty good crystals, but ground crystals we used were extremely good. But this is a macrogravity grown. You can see that the detectivity doubled, 4.20. And we checked this work was measured, the detectivity was measured because we could have developed the system here in our lab, which involves a lot of sophisticated optical instruments. But there is a company in Connecticut called Barnes Engineering, which is the leading company in America who makes iron detectors. We actually had an agreement with them that they will do our testing at no charge. So we flew to Connecticut and worked in their lab for a week, and they make detectors out of this crystal and measure the detectivity and so on.
So why was this SL3 lower?
Because there was a problem in that. As I mentioned, the crystal growth was not very uniform. So we had trouble with the instrument, the power fuse went out and there was very little time left, and it was bad. That's why we flew this experiment again. And this is another 2 experiments were done. So in both cases, this was about 2 times better. This diagram actually tells you detectivity of various crystals, and if you look at the IML, this is one microgravity, this is also microgravity, this is a seed crystal. This gives you as a function of the D star as a function of the frequency, and one can see this. This is an interesting diagram. The interferograms, these are Mach-Zehnder interferograms reconstructed from the holograms in the flight cell. If you look at this diagram here, these are iso concentration lines. If the seed crystal is here, when the seed crystal is growing, the concentration of the fluid is changing. You know, concentration is higher here and lower here. So these isoconcentration lines indicate that the fluid field is very uniform. And this is also a picture taken at a later time, and this is also a similar picture. And the MET means the mission elapsed time in the shuttle mission. This is taken at 117 hours, this is 11 hours, and this is 125 hours. This picture diagram shows, this is a picture on the ground. If you take this Mach Zehnder pictures on the ground, because of the gravity, the concentration field is driving towards the ground, vertical. So the isoconcentration lines are no more isoconcentration, they are actually going like that. And this is in space. This is a real picture. This picture actually was put on the cover page on the Laser Focus magazine in 1991. On this Space Lab 3, so this was actually, so you can see that this actually gave us a good idea that a similar thing, if this experiment and this, when the pictures were taken like this, if the astronauts perform on the treadmill, then the G changes. And we could see, I don't know whether we have any more pictures here, we don't, but lots of pictures were taken like that. But if you do that experiment and take this interferogram at a time when the astronauts are performing the treadmill, then these isoconcentration lines were skewed towards the gravity gradient. And that tells us immediately that at this time the astronauts were on the treadmill. And at that time also the shuttle was maneuvering and the thrusters were being fired, which we have a complete record. Minute by minute, second by second, we have a record for the entire 7 days. So this is a very useful thing to determine. I don't have a picture here for the particles, but if I take a similar picture where the particles were floating in the crystal, you could see that the particles. And this is the first time we calculated that the G values in the space shuttle at that time was on the order of 1 × -6 G. So this was a very useful technique by which we could determine the fluid velocity. By the particle motion, we could determine the fluid velocity. And the reason the particles were of different sizes, because we don't want to put the particle sizes so there was no Brownian motion in the system. This is a real fluid velocity measured for the particles which are there. We also did high resolution synchrotron X-ray diffraction measurements at the Brookhaven National Lab. And the purpose of this was, objective of this was, general to check the lattice regularity, that how the molecules and atoms are aligned in the crystal, identification of inclusions, because if there are defects in the crystal, either they are air inclusions or particle inclusion, then the diffraction pattern will show us the effect, growth mode and stability, interface location. You see that if there is a crystal, if this is a crystal for example, and if this is a seed here, red part, and this is a grown crystal, so there is a boundary here between the seed and the new growth. So the X-ray diffraction technique actually can tell us where the interface is. So the purpose of the X-ray diffraction was to determine where the interface of the crystal is. So the location of the interface, and specific.
Now, you say it can be used for identification of inclusions and dislocations. Are you talking about the total dissociation of the initial reactants?
No, the dislocations produced during growth. Only dislocations during growth, not the total.
Of the seed?
No, the grown crystal.
Okay, of the grown
crystal. We took the diffraction pattern in the grown crystal there, of the crystal, and we could see that. We can determine dislocation and locate dislocation positions by X-ray diffraction technique.
And the X-ray diffraction technique can also be used to understand that the original reactants have been totally dissociated, right?
Yeah, that's correct. And specific to this flight was the characterization of the potential seed crystal as the basis. So we did all this work on the seed crystals as well as the new crystal. So we have a complete data side by side and what the seed crystal look like and what the new growth looks like. Characterization of the space growth crystal, location of the seed space interface, and comparison of the space growth crystals and control ground crystals. This is an interesting picture. This is a actual slice cut from the flight grown crystal of IML-1. If the growth was, for example, here, we cut a slice parallel to that face, and if you look at it, this is somewhere here should be the seed crystal, and then the new growth is up here. So if I use X-ray diffraction technique, I should be able to locate if there is a crystal grown on the ground. I should be able to see the growth interface right at this point. But in this slice, we could not locate. And that shows that the transition from the growth to dissolution to growth was very, very uniform. And I could not locate anywhere. This is, although there is a shade change in the color of the topograph, but we could not locate the interface. So that actually tells us that the crystal was very high quality. So we'll show you this picture first. This is a picture of a crystal, X-ray diffraction picture. You can see that the defects gives you the darker part. That means they are all defects in this crystal itself, all this here. Even if I see this crystal, here you see that this was the starting seed. And this was the new growth. You can see that the starting seed, the interface between the new growth and the old seed was pretty distinct. And this is on ground crystal. That means that the transition from dissolution to growth was not very uniform. And I could locate, this indicates that there are a lot of defects on this crystal here at this point on the interface. So this is a very nice technique. This work was done by, actually this is not on the synchrotron radiation topography in Brookhaven. This was done in Paris, France, because there is a very well-known scientist there by the name of Dr. Hothier. He's at the institute there, and we took our crystal to his lab because he has a very sophisticated technique of doing this. This is the result of X-ray diffraction. The surface morphology, the surface was substantially uniform, faceted edge growth at different rates. Internal character, the lattice orientation of the crystal was accurate to 1 to 2 arc seconds. That means the whole lattice of this crystal was very, very uniform. The distortion orientation was correct to the order of about 1 to arc second, and that is the kind of orientation you see in silicon crystals. The silicon crystal, which is almost people can grow with no dislocation, have that kind of a lattice orientation. Polycrystalline inclusions were measured in X-ray diffraction. You could see the particles, because wherever the particles were, you could see the field around it. Very few crystallographic defects, no prominent growth relative to dislocations in the speed grown crystals, very few surface treatment related edge dislocations were seen. The interface is scarcely visible. You could not see the interface of the seed and the new crystal.